On April 10, 2019, astronomer Shepard Dolman stood in front of the world's media and revealed an image that should not have been possible to capture. A photograph of a black hole. It's not an artist's rendering, not a simulation. It's an actual image of the event horizon, the boundary where space-time curves so violently that nothing, not even light, can escape. The black hole was 55 million light-years away, at the center of a galaxy called Messier 87. It was 6.5 billion times more massive than our Sun. And the photograph showed exactly what Einstein's equations had predicted over a century ago. A ring of light surrounding absolute darkness. The photon sphere where light orbits the black hole's edge before either escaping into space or falling inward forever. But the image was not just a confirmation of theory. It was proof of something far more disturbing. Because black holes do not just bend light, they bend time. They distort reality itself. And the ring of light in that photograph was not emitting from the present moment. It was emitting from multiple time periods simultaneously, warped by gravity into a single visible structure. Which means when you look at a black hole, you are not looking at an object. You are looking at the edge of the universe's operating system, the place where the rules break down, where physics transitions from equations we understand to singularities we cannot explain. And the fact that we can now photograph this boundary means we can study it, can measure it. And we can ask the question that has haunted astrophysics since black holes were first theorized. What happens when reality collapses into a point of infinite density? And what does that tell us about the universe we think we understand? Black holes are not mysteries because we do not know they exist. We have detected thousands of them. We have measured their masses. We have tracked stars orbiting invisible companions, moving at speeds that only extreme gravity can explain. In 2020, astronomers Andrea Ghez and Reinhard Genzel won the Nobel Prize in Physics for proving that a supermassive black hole for 1 million times the mass of the Sun exists at the center of the Milky Way by observing stars whipping around it at nearly 2% the speed of light. The mystery is what they are. Because black holes are not objects in the traditional sense. They are regions of space-time where gravity has become so intense that the fabric of the universe itself is torn. Albert Einstein's general theory of relativity predicts that when enough mass compresses into a small enough volume, space-time curvature becomes infinite. The mathematics break. The equations produce infinities. And physics, which is supposed to describe reality, stops making predictions. This is called a singularity, a point where the known laws of nature cease to function. And every black hole contains one. The event horizon, the boundary visible in the 2019 image, is not the singularity itself. It is the point of no return. The radius where escape velocity exceeds the speed of light. Cross that boundary, and you are no longer part of the observable universe. You are cut off from causality. You cannot send signals out. You cannot climb back. You fall inward, inevitably toward the singularity at the center. But what happens there? What occurs when matter is compressed into infinite density? Does it disappear? Does it tunnel into another dimension? Does it create a new universe? Physics has no answer. Because the singularity is hidden behind the event horizon, and no information can escape to tell us what happens inside. Except that in 2019, we photographed the edge. And the photograph revealed something that Einstein himself found so disturbing, he spent years trying to prove it could not exist. The idea of black holes began in 1915 when Karl Schwarzschild, a German physicist serving in World War I, solved Einstein's newly published field equations of general relativity. Schwarzschild was stationed on the Russian front, calculating trajectories for artillery shells, when he became fascinated by Einstein's work. He applied the equations to the simplest possible case, a spherical, non-rotating mass in empty space. And he discovered that if you compress any amount of mass into a small enough radius, space-time collapses into a structure with an event horizon. Einstein hated the solution. He believed it was a mathematical artifact, a quirk of the equations that had no physical reality. He argued that nature would never allow matter to compress to such extremes that some unknown force would intervene before a singularity could form. But Schwarzschild's math was correct, and over the following decades, astronomers began to suspect that these objects were not just theoretical. In 1964, physicist John Wheeler coined the term black hole to describe them. And in 1971, astronomers detected the first candidate, Cygnus X1, an X-ray source in the constellation Cygnus that appeared to be a massive invisible object pulling gas from a companion star. The infalling gas heated to millions of degrees, emitting X-rays before crossing the event horizon and disappearing. It was the signature of a black hole feeding. But detecting X-rays from infalling matter was not the same as seeing the black hole itself. For that, astronomers needed to photograph the event horizon. And the problem was scale. The supermassive black hole at the center of Messier 87, designated M87*, has an event horizon diameter of about 40 billion kilometers, roughly the size of our entire solar system, but at a distance of 55 million light-years. That diameter subtends an angle of only 40 microseconds as seen from Earth. That is the equivalent of photographing a grapefruit on the surface of the Moon. No single telescope on Earth has the resolution to image something that small, which is why astronomer Shepard Dolman proposed something that had never been attempted. He suggested linking radio telescopes across the entire planet, using a technique called very long baseline interferometry to synthesize an Earth-sized virtual telescope. By coordinating observations from dishes in Hawaii, Arizona, Chile, Spain, Mexico, Antarctica, and the South Pole, and combining their data using atomic clocks precise to within billionths of a second, astronomers could achieve a resolution sharp enough to image the event horizon. The project was called the Event Horizon Telescope, and in April 2017, the array activated. For 10 days, 8 observatories around the world pointed at M87* simultaneously, recording petabytes of data on hard drives because the information flow was too massive to transmit over the internet. The drives were shipped to supercomputing centers in the United States and Germany, where teams led by computer scientist Katie Bouman developed algorithms to process the data, correcting for atmospheric turbulence, clock drift, and the rotation of the Earth. It took 2 years to generate the image, and when it was finally revealed in 2019, it looked exactly like the simulations predicted. A bright ring of light, orange and yellow, surrounding a dark central shadow. The photon sphere, where light from the accretion disk orbits the black hole before either escaping or falling in. But the image was not symmetric. The southern side of the ring was brighter than the northern side, and this asymmetry was not random. It was caused by relativistic beaming, a consequence of the fact that the accretion disk is rotating at nearly the speed of light. The side of the disk moving toward Earth appears brighter because the photons are Doppler shifted to higher energies. The side moving away appears dimmer. This was proof that the black hole was rotating, spinning, dragging space-time around it in a phenomenon called frame dragging, where the fabric of reality itself is twisted by the black hole's angular momentum. Why does space-time spin with the black hole instead of remaining stationary? Until now, this looked like a technological triumph, confirmation of general relativity. An image that proved Einstein's century-old predictions were correct down to the smallest observable details. But it was not a confirmation, because when astrophysicist Avery Broderick at the University of Waterloo analyzed the structure of the photon ring in the 2019 image, he discovered something that should not have been there. The ring was not smooth, it was not continuous. There were brightness variations, hotspots, regions where the emission was far stronger than the average. And these hotspots were moving, orbiting the black hole at speeds exceeding 99% the speed of light. These were not anomalies. They were features of the accretion disk, clumps of superheated plasma spiraling into the event horizon. But their presence created a problem, because according to general relativity, as matter approaches the event horizon, time dilation becomes extreme. An outside observer watching an object fall toward a black hole would see it slow down, redshift, and freeze just above the event horizon, taking an infinite amount of time to cross. But the hot spots in the M87* image were moving. They were crossing the photon sphere. They were falling inward in measurable time, which means either general relativity's prediction about time dilation is incomplete, or the event horizon is not where we think it is. This is the hidden barrier. The theory that predicted black holes also predicts that we should never see anything cross the event horizon, yet the 2019 image shows material visibly spiraling inward, disappearing into the shadow. The observations contradict the equations. And then, in 2020, astronomer Michael Johnson at the Harvard-Smithsonian Center for Astrophysics published a study analyzing the substructure of the photon ring. He demonstrated that the ring is not a single feature, but a series of nested rings. An infinite sequence of increasingly faint images created by light that orbits the black hole multiple times before escaping. Each ring represents photons that circled the event horizon one additional time, creating a fractal-like structure that encodes information about the space-time geometry around the black hole. Johnson's analysis revealed that if the Event Horizon Telescope's resolution could be increased by a factor of 10, these subrings would become visible, allowing astronomers to test general relativity in the most extreme conditions ever observed. And any deviation from Einstein's predictions would suggest that black holes are not described by general relativity alone. That quantum mechanics, the physics of the very small, plays a role at the event horizon. This is the frontier. The place where gravity becomes so strong that quantum effects can no longer be ignored. And if quantum mechanics modifies the structure of the event horizon, it might resolve the most disturbing paradox in black hole physics, the information paradox. Why does quantum mechanics forbid information from being destroyed, but black holes appear to destroy it? In 1974, physicist Stephen Hawking published a calculation showing that black holes are not completely black. They emit radiation, a quantum effect caused by particle pairs forming at the event horizon. One particle falls into the black hole, the other escapes as Hawking radiation. Over unimaginable timescales, trillions of years, this radiation causes the black hole to evaporate. But the radiation is thermal, random. It carries no information about what fell into the black hole. Which means if you throw a book into a black hole and wait for it to evaporate, the information contained in that book is lost forever. This violates the principles of quantum mechanics, which require that information is always conserved. It's always retrievable, even if scrambled beyond recognition. Hawking himself believed the information was destroyed. But in 2004, he reversed his position after physicist Leonard Susskind and others demonstrated that information might be encoded on the event horizon itself in a holographic structure where the three-dimensional volume of the black hole is described by information on its two-dimensional surface. The holographic principle suggests that the event horizon is not a smooth boundary, but a quantum foam, Planck scale structure where space-time itself is pixelated, granular, fundamentally discrete. And if this is true, then the 2019 image is not a photograph of emptiness. It is a photograph of the universe's hard drive. It's a place where information is stored when reality compresses. In 2022, the Event Horizon Telescope collaboration published a second image. This time, the target was not M87*, but Sagittarius A*, the supermassive black hole at the center of the Milky Way. The object that Andrea Ghez and Reinhard Genzel had spent decades studying by tracking the orbits of nearby stars. Sagittarius A** is much closer than M87*, only 26,000 light-years away. But it is also much smaller, 4 million solar masses compared to M87*, 6.5 billion. And critically, its accretion disk is turbulent, chaotic, changing on timescales of minutes rather than days. Imaging it required combining data from multiple nights and using algorithms to average out the variability, creating a composite picture of the black hole's average structure. The image, when revealed, was nearly identical to M87*. The same bright ring, the same dark shadow, the same photon sphere structure. But this time, the data included polarization measurements, information about the orientation of light waves as they escape the black hole's gravitational field. Astronomer Monika Mazza-Brodska at Radboud University led the polarization analysis. She found that the magnetic fields around Sagittarius A** were not random. They were organized, threaded through the accretion disk in spiraling patterns, channeling plasma into jets that, in other black holes, shoot out at nearly the speed of light for thousands of light years. Sagittarius A** does not have large jets. But the magnetic field structure suggested it once did. That the black hole at the center of our galaxy was once far more active, consuming stars and gas at a rate thousands of times higher than today, launching relativistic jets that might have sterilized any planets too close to the galactic core. And then in 2023, astronomers using the James Webb Space Telescope detected something that had never been observed before. a ring of molecular gas located just outside the influence radius of Sagittarius A*, where the black hole's gravity dominates over all other forces. The gas was cold, dense, and chemically rich, containing the building blocks of organic chemistry: carbon monoxide, formaldehyde, methanol. Astrophysicist Farhad Yousefzadeh at Northwestern University analyzed the data and found that the gas ring was not stable. It was fragmenting, collapsing into clumps that could potentially form stars. But these stars would be born in the most hostile environment in the galaxy, orbiting a black hole that could tear them apart with tidal forces if they ventured too close. This was the proof that black holes are not just destroyers. They are sculptors. They shape their environments. They regulate star formation. They drive the evolution of galaxies through feedback loops that balance the inflow of gas with the outflow of energy from jets and radiation. And the most unsettling realization is that every large galaxy has a supermassive black hole at its center. Not as an occasional feature, as a rule. The mass of the black hole correlates directly with the mass of the galaxy's central bulge, as if the two grew together, locked in a relationship where the black hole's gravity controls how the galaxy forms stars and the galaxies. Stars feed the black hole. We do not live in a galaxy. We live in a system organized around a singularity. On April 10, 2019, Shepard-Dolman revealed an image that humanity had dreamed of capturing for a century. He did not know he was documenting the boundary of reality itself. He thought he was photographing a black hole, but the image showed something far stranger. It showed the place where time stops, where space folds, where the known laws of physics give way to mathematics we do not understand and predictions we cannot test. The event horizon is not just the edge of a black hole. It is the edge of knowability, the point beyond which observation becomes impossible and theory becomes speculation. And the fact that we can now photograph this edge means we can measure it. We can watch material fall toward it. We can study how light bends around it. We can test whether Einstein's equations hold in the most extreme conditions the universe allows. But we cannot see what happens inside. We cannot observe the singularity. And we may never be able to. Because the event horizon is not just a physical boundary. It is an informational barrier, cosmic censorship that prevents the universe from revealing its most fundamental secrets. Which means black holes are not anomalies. They are the rule. They are where the universe shows its true face, where reality admits that it is not continuous, not smooth, not infinitely divisible, where space-time reveals that it has a structure, a breaking point, a limit. And once you realize that black holes are not isolated objects, but central features of every galaxy, that they regulate star formation, drive evolution, and shape the architecture of the cosmos, you start to understand that the universe is not built around stars. It is built around singularities. And we are living inside a system we barely understand, orbiting a darkness we can photograph but never explain. Subscribe to Universe Uncovered, because the universe is not infinite. It has edges, and we've finally seen one.